Hello, Hangprinter community. I just wanted to share the progress on the auto calibration work. I've been working with this simulator for a year now, and I've always wanted to be able to calibrate a hang printer, or in this case, a slide printer, which is a 2D hang printer. I've always wanted to calibrate it based on only motor encoder values and some mechanism or some way to set line tightness. So having only those two things, the ability to make the motors wind in line and the ability to read the motor position, I want to be able to calculate where are the anchors. And I only want to press one button. That's always been the dream. And I think I've achieved it today. This is a Python script, a crazy complicated numerical thing with the 4 optimization loops at least in and very complicated cost functions and filtering and stuff live inside this script. So we invoke it from the terminal, and in this case I tell it we're working with a simulated slide printer. If I had another machine, I would say Hangprinter 3, Hangprinter 4, or more advanced Hangprinters are also supported. I tell it to run in the full auto mode, so it just makes its own decisions about where to collect data and if it needs more data or not. And I also tell it to speed up the simulation by 35x so that this demo won't take so long. I'll just start it now. And the script will start by doing some noise calibration. You can see the colors of the lines are flickering. When they are dark orange, it's a slack line. When it's yellow, it's a tight line. And these lines have these are flexible lines, and they have lots of physical stuff like friction. Now it's tuning how much force it needs to use in order to pull the mover around without trying to go beyond the limits of the reachable volume. And the dream has been that we can, now it's collecting data, and I'm injecting some disturbances here just to show you that the numerical methods I've implemented are very robust. If there are disturbances in the data, it can actually auto detect that and discard those data points or downweigh their importance, which is it's a very big feature to have, because in real life data is always noisy and data is always too bad, but we still want it to just work, which is quite a lot to ask, of course, but I think I achieved that. It has taken at least a month more than I anticipated. Okay, so let's give it 3 broken data series, so there's no unbroken data series or sweep, as I call them. There's no good sweep here, it's just the 3 broken ones, and it just needs to work with those or decide that they were not good enough. It will keep trying regardless, I think, because it doesn't know what is good for this machine and what is bad for this machine. So it found a solution. The cost was almost 17, which is a very high cost. These are normalized costs, so on every machine the cost will be interpreted in the same way. A cost above 10 is concerning. That's probably a bad fit. And a cost below 5 is good or usable. And if you get below 2, then it's a fantastic fit. So we see now it got an undisturbed sweep because I was talking so much. Let's see what it will do with that. Okay, it got slightly better, but still too bad. It resets its patience every time it finds a new best one. So this one was better than the previous one, and therefore it still has patience for 3 more attempts, just as it had before. Let's disturb the data. Okay. This demo is kind of unprepared, so I don't know what to expect. But I have made hundreds and hundreds of tests, so it should get closer. It gets closer. We're nearing into a usable calibration. We always disturb it like that. Disturbances, disturbances. Okay. We have to have lots of patience to do this, but at least we don't have to crawl on the floor with a measurement tape. And we don't have to know lots of stuff. I just sent one command and it did all its stuff. The user will just watch the machine move around and some numbers get printed. Hopefully they won't even have to look at the numbers. Ideally they will just have to watch a lamp turn green or something. Okay, still improvements. It collects lots of data this time. It usually converges much quicker. But as long as it's making progress, you know. It will decide by itself where to go, where it thinks its hole in the dataset are. So it decides whether to go up, left or right to make the next sweep. Which is interesting. We have an even steady march towards low costs. Let's see what happens. Oh, this wasn't better, this was worse. So it keeps trying. Disturbances, disturbances. Maybe I disturb it more than I usually do. It's easy to get lazy. So that was sweep number 8. That's a lot of sweeps. To get all the detail logs, we could look at this log, but it's so noisy. And I would have to explain a lot of theory to even understand what's in there, to help you understand. Let's see, can we get the cost lower than this? Maybe below 2 would be nice. Oh no, it's worse. Okay, let's just kill it and see what we got. In real life, I would just let it run until everything's perfect, of course. Or at least until everything's kind of good. But we have the option to stop it whenever we run out of patience ourselves. Okay, this is the last attempt. Should we give it? Should we give it? Okay. We give it the last attempt. even though it does all this filtering and stuff, it's still much faster per solve per run compared to the previous method I used, which is nice because it has to do it 7 times. It gets slower and slower the more data points we collect, and now we have collected several hundred of them. So that's why it feels so slow now. Okay, it was worse. Okay, time to see the solution we found. It says it's good quality, and the interpretation is that it's between 2 and 5, which is good, acceptable quality. And yeah, this is about the noise model, internal stuff. But since this is a simulation, I know what these numbers, the theoretical perfect numbers are. So a 0 here is perfect. This should be 1900. So we were 1.8 millimeters off. And this should be 1645, 0. So we are 1.7 millimeters off. And this should be 950, so we're 0.94 millimeters off. And these are just mirrored numbers, so we're 0.9 off and 0.3. So we're below 2 millimeters in error on all the parameters, which is fantastic. And it did send the calibration command to the machine. It's currently running RepRap firmware here on my host machine, which is nice. So this slide printer here is now calibrated according to these values. I can't actually give it a G-code and prove to you it works, but it does. I did offline. It just takes a few minutes. Okay, happy demo. This was a great one. See you later. Bye.